from the college.
I again welcome you, sir, and I request you to kindly commence the session.
You need the Welcome everyone. This is a topic on power amplifiers, and this is the actual research work that we have done. Actually. So I thought this is actually so I am primarily in antennas, but this is one of the most cutting edge work that I think it is the most one of the most cutting edge work that we have done, and that's why I wanted to show this because antenna, lots of papers are there, lots of work has been done. So uh, okay, so this is the schematic of a power amplifier. Okay. So power amplifiers are used in many places, especially for 5G. They become very important because for the 5G standard, there is a special modulation scheme called OFDM, where you have very narrow bands, and the amplifier has to provide amplification both at peak power as well as what we call back off power. So somewhere between zero and the peak. So the power amplifier has to perform at both the power points, both at the peak power as well as the average power. So, and because of this property, we need some special amplifiers. So one of the requirement of power amplifiers is to increase the efficiency. So what do we mean by efficiency? Efficiency means the percentage of the input power, that is the DC power, that is actually transmitted outside. And in a power amplifier, ideally we would like all the DC power to be transmitted outside. So that is called 100% efficiency. But we don't get that. And based on the efficiency, you might have known various classes of amplifiers that we get, like class A, class B, class C. And that is still going on. Okay, I mean it didn't stop. So the class A, B, I think is around 100 years old, and class E is 50 years old. But since that it didn't stop. Research on power amplifier has been continuing, and every time a new standard comes, some new power amplifier with more efficiency is required. So this our work actually is in this regard to find a power amplifier that caters to 5G standard and also provides high efficiency. So this is the general schematic of any power amplifier. You have an input signal, you have an output signal, you have a DC supply, and this is the main power amplifier core, which usually consists nowadays gallium nitride has become the standard, and gallium nitride transistors have their GP, the power gain, and the eta D, which is the efficiency. So these are the two things that matter for a power amplifier: the gain and the efficiency. Now, suppose this is our transistor, then we need an output matching network and input matching network. So I hope everybody knows what is matching. Matching means to ensure that maximum power is transferred. So input matching network also performs that same function, that maximum amount of power from the source goes to the input of the transistor, and output matching network ensures that maximum amount of power goes from the output of the transistor to the load. That's all. So ideally, your power amplifier should have a curve like this. So this is the voltage waveform, this square, this rectangle, and this dotted one is the current. So if the current flowing through this transistor and the voltage across this transistor don't overlap at all, then you get 100% efficiency. Isn't it? Because power is current multiplied by voltage. So if the current is zero when the voltage is high, and the voltage is zero when the current is high, then ideally no power should be dissipated in the device. And this is what we want to achieve, by the way. This is our I told you, right? Every year somebody keeps publishing some paper on higher efficiency. It's basically to achieve this goal, that we should have perfectly separated current and voltage waveform, but it is not that easy. In fact, it is impossible. What we can achieve is something that is near to this. So these are the equations of a power amplifier. So this is the output. If I max is the maximum current, drain current, and VDD is the maximum voltage across the device, then the output power at various harmonics is given like this. So these are the first part of this talk are the things that are already known. You can find it in some book, but just I will give a overview. So for example, for a particular power amplifier, a real power amplifier, the drain efficiency might come out to be 81%, but not 100%. So these are some of the characteristics of a power amplifier. This is the, for example, the ID, the current flowing through the drain versus the voltage across the drain. And these are the time domain waveforms. So these are, you can find these curves in any book. Um, so in general, the output power in terms of voltage and current is given by this equation. And these are the expressions for the transducer gain and operating power gain. So, the power gain of a power amplifier, it can be defined in many ways actually. For example, let's take this an example. You buy a source which can supply 10 watts and you have an output power which is 100 watts. Then what is the power gain? It is 100 watts divided by 10 watts, which is 10. This is what we actually want, that we buy a source which is 10 watts from the market and we deliver 100 watts. Then this is how we calculate the gain. But what if the total power inputted into the power amplifier is not 10 watts? It is say lesser than 10 watts. Then what is the gain? So based on that, this GT, so GT is the one that I just described. The output power by the total power capable, the input source is capable of delivering. But you can also define the power gain in terms of the power that is delivered to the load divided by the power that is actually entering the amplifier. So this are definitions of the GP and GT, and you can basically, we can, for example, this is a particular type of power amplifier where you can, based on the conduction angle, theta, you can find out the IDS, the drain current, and also the efficiency. Okay, so this is the general formula for the efficiency in terms of the conduction angle alpha. Okay. So if we go back a little further, we can actually keep writing the expressions for the drain current, the voltage across drain to source voltage for various classes of amplifiers. So for example, for a class B amplifier, these are the expressions for the drain current and drain voltage. For a class F amplifier, these are the expressions. So similarly, this is the expression for the drain current in a class F inverse, and this is the drain to source voltage in a class F inverse amplifier. So then these are the characteristics, corresponding character. In the previous slide, I had shown the equations, and these are the current and voltage waveforms. This orange line is the voltage waveform for class B, and this blue line is the voltage waveform for the current, is the waveform for the current. And similarly, these are the expressions for the DC power, and so this orange line is the DC power output and this blue line is the efficiency. So For a class B, we know that the conduction angle is 180 degree. But these curves, you see so many curves because we kept changing the value of alpha and we got all these curves. Similarly, the case for class F. So when we try to fix a particular class of amplifier, how do we do that? So there is a particular design tool which is known as load pull analysis. So I, so what we do in a load pull analysis is we keep changing the load of the amplifier. Okay, we do a sweep of the load to all possible values, and based on the one that suits our voltage and current waveform, we choose that. So we adjust our bias voltages based on the value of the load pull sweep that we do. So this is an algorithm of how we get the various classes of amplifiers. For example, in the first cut, a fundamental load pull is done. Then we do the load pull for the second and third harmonic and so on. Now, one thing about a power amplifier design is that we think that only the input fundamental frequency goes in and we get an output frequency which is at the same value. So the output frequency ideally should be same as the input frequency. But due to non-linearities, what happens is that the output also contains harmonics. And these harmonics actually have a very important role to play. For example, in the previous slide, say let's consider this F class F amplifier. You see that this orange line is the voltage, right? Now, ideally, if there were only fundamental harmonics, then this would be a sinusoidal curve. But because of the presence of higher order harmonics, we get this characteristic square shape. It is not a perfect square, but somewhat near. So these harmonics, though undesirable, these actually play a very important role in shaping the various waveforms. I'll just open the equation. It's getting a little hot. So this one, so these harmonics, as I said, are the primary tools that we use to shape these current and voltage waveforms. So when we do that load pull analysis, we not only do it for the fundamental, so we sweep all possible impedances for the fundamental frequency and also for the higher order harmonics. So for the second harmonic and third harmonic. Usually because an HEMT is a square law device. So the second harmonic becomes very important because if a device follows the square law, then it is more likely to produce the second order nonlinearity. So that's how we did it here. And these are sort of is everybody familiar with what a Smith chart? Okay. So this is a Smith chart. It represents all passive impedances, okay? And this blue line represents all the second order load pull values. This orange line represents the fundamental frequency load values, and this black line represents the third harmonic. Okay. So this is how we design, say, a class B or J amplifier. Okay, and these are the various values of the load that we need to achieve this class B and G. So these values are obtained from load pull analysis. Once again, load pull means we sweep all the values in this Smith chart and select only these values. Now, what we did, now this is what was done traditionally. Okay, traditionally, I mean, what was found is that, so you know that the top half of the Smith chart is inductive and the bottom half is capacitive. If we just follow this load choice, then what happens is that the top half and bottom half, if you choose, say, loads along this half or along this half, then they should give equal efficiency because they are symmetric. But in practice, this is not what happens. In practice, what happens is if you choose load in the upper half that is inductive, that gives a different efficiency as compared to the bottom half. So this work that we did, uh, what we did was to find a model of why this is happening and explain this phenomenon. So we chose three different cases. Okay. One is when our conduction angle is 180 degree, that is when the amplifier is a pure class B amplifier. The next is the maximum conduction angle and minimum conduction angle. Yeah, so we see the voltage and current waveforms for the three cases. Okay, so this blue line is the waveform for case 1 when it is a class B, and as you can see that this blue line has 180 degree conduction angle. It's like a half wave rectifier for the case 1, and for the case 2, this orange line is there. That is when we choose the maximum conduction angle, and this for the black case 3, we have this black line. Let me know if anybody is not following what is going on here. So, as I said, this is one of my favorite works actually because it took a lot of effort. So once again, these are just curves for various conduction angles. Okay, so this orange is for maximum conduction angle, and the black is for minimum conduction angle. So this is the device that we selected. This is a gallium nitride model transistor that is given by Cree. And this curve represents the nonlinearities. So gamma represents the amplitude nonlinearity, and phi 2 represents the phase nonlinearity. And if we keep the second order harmonic reflection coefficient fixed, magnitude fixed at 0.9, and keep changing its phase, then this is the various values of gamma and phi that we obtain. Okay. So the work that I'm describing is based on another paper that was published where they did a similar analysis. So the equation for the drain current is given like this. Okay. They started from here. So you see what is happening is that we, instead of seeing what the device does, and so suppose let's take a simple case. Suppose I ask you to make a circuit using op amps. Suppose I ask you to make a non-inverting amplifier using op amp. How do you do that? You first take the op amp, you put the load, and then find the values of the feedback resistances, and then you find out the gain, right? Here we are doing the mathematics first, and then we are adjusting the circuit to fit that mathematics. So the mathematics is this equation, that the drain to source current is given by a combination of the fundamental and the second harmonic. The second harmonic has this term gamma, which represents the amplitude nonlinearity, and phi 2, which represents the phase nonlinearity. And then we plot this contour graph. Okay, so this contour graph is actually the plot of various conduction angles and what the value of phi 2 and gamma will be for those conduction angles. So this black line is a line where the conduction angle is uniform, is 0.3. So it takes some time to achieve this. It means it's like suppose you have amplifiers, 3 amplifiers or infinite number of amplifiers which have the same conduction angle but different nonlinear parameters. then what would be the values of those non-linear parameters? This equation. Okay, that's how this is made. So this one was published in 2019, and we did our modeling for that load, optimum load based on this load. So, so conventionally, the class B amplifier that we chose, that is present, has a model like this. Okay, this is the drain current, and this is the drain to source voltage. Uh, and these are the loads for the various cases. So, for example, for case 1, which is the simple class B amplifier, this one, this is the load that we choose, which is what I have already shown. But if we take it to the second case, that is for maximum conduction angle, then you see that this orange line becomes this gray line. And for the third case, which is minimum conduction angle, this orange line becomes this dotted pink line. So the modeling philosophy that we chose was this. We make the second harmonic purely imaginary and take the first harmonic load as a complex load and take the third harmonic load as 0. So once we do this and then write down the equations, we get this kind of curves. Okay. So this is case 1 for this. So this is case 1. This is for simple resistive load. This is for inductive load. This is for capacitive load. So once again, unless you actually means I don't have the time to explain step by step how we get these curves from these equations that I just described. But this is what happens. Okay, and these curves that we these are theoretical curves. Okay, like if this is the mathematics, then how the drain current and voltage, drain to source voltage should be. So this is what we get from the mathematics, and then if we calculate the efficiency for the various cases, we see that for the capacitive case, when we have a capacitive load, we get a higher efficiency. So this phenomenon was observed, okay, that when we have a capacitive second harmonic load, then the efficiency is higher for the same magnitude. So right, in electrical engineering we see duality of everything. That if we have a capacitor and inductor, if both have the same magnitude of reactances, then they should give the opposite effect. But that was not what was being observed, and this was unexplained so far, that why it is not happening. So using the model that we proposed, we can clearly, using the formulae that we developed, we could explain this case, that for a capacitive value we have higher efficiency. Okay. So that is the main conclusion, okay, of this work. And now this was the mathematics part. Now just showing the mathematics and proving something doesn't validate. We have to also actually make the power amplifier. So this is where we are making the amplifier. So we choose, so this is the gallium nitride device. This shows the entire design space. These are PAE contours. That is, in this space, the PAE power added efficiency is nearly equal. Similarly, this is the output power contours. So in this shaded region, the output power is nearly equal. And we choose all our cases, the case 1, case 2, case 3 loads based on these load pull curves that we get. And now these are the simulations of the actual device. Okay? So the previous ones that I showed were from mathematics, and these are the actual device simulations. And we see that they are quite similar. What we predicted using our formulae and what we actually get are quite similar. And yeah, this is again the simulation of the efficiency, but this is now with the actual device as compared to previously when we were just dealing with equations. And finally, this is the fabricated power amplifier. This we tested in our lab. And finally, so we tested it three ways. One was a DC test. So this is using multimeter where we just test what are the DC voltages and currents. Then this was using VNA. So VNA does a non-linear measurement. It calculates the S parameters which are just the non-linear. It doesn't take into account harmonics. And the third step was to do a complete harmonic test with actual input signals and actual output signals. So this was another test we did on the power amplifier. This is for pre-distortion linearization. So this is as needed to show that this is a real power amplifier which can be linearized. So I'm sure everybody knows what is linearization and what is to make a non-linear system linear is called linearization. Now, one effect of non-linearization is spreading, spectral spreading. You might be knowing this, that if we pass a spectrum through a non-linear system, at the output, the spectrum spreads, the frequency spread. So this is the output, this red line was what was happening before linearization. And after applying the pre-distortion linearization, this is this blue line. So this red line got reduced here. So this is an actual 4G LTE signal, okay, that was produced using a digital signal generator. And so this is the proof that this algorithm works. And finally, this is a comparison of our work. Actually, our work is not a design work. It was not really meant to show that it is providing good work. It is just a methodology. And using that methodology, we got these results. Uh, One other work that we did, based similar, not similar, it was derivative of this, is uh, is to is to solve the problem of double inflection of the AM distortion. Okay, I'll explain word by word what I said. So AM distortion is a measurement done in a power amplifier. So AM means that for ideally, if you apply some power at the input, the output should be proportional. But in reality, that doesn't happen. The output is not proportional because there is nonlinearity. And this distortion is called AM distortion. So ideally, any amplifier should have this line. If I plot the AM distortion, it should be zero, ideally. It should go on zero for all output power levels. But in reality, what happens is it goes down. The output power goes down and this distortion appears like this. Now in this class F inverse amplifier, this distortion is manifested in two ways. There is a this is called a double inflection point. So there are two dips, one dip here, one dip here. And this we solved using the methodology that I just described. So we have developed a new class of amplifiers called IF inverse, where there is inflection, but a single inflection point. So then is it just to count the number of inflection points? No, it's to ensure that the distortion happens at a higher power level. Instead of the distortion starting at say around 20 dBm output power, now by correcting this double inflection, our distortion starts at a higher power level, at 35 dB. So how is it done? So see, we started with this same graph that I described for the gallium nitride a few slides back, and the same nonlinear model that we used. Now the trick here is to have a drain current which is proportional to that formula and minus a certain constant. Okay, so that's the thing. If you have a drain current which is proportional to the formula that I showed, and you subtract from it a constant value, then you can show using the model that we developed that inflection points will go. And so this is the curve that we got. Okay, so see, for various values of theta, okay, so this is a complete 360-degree sinusoidal phase. This is what happens in a F inverse, because of which we get the double inflection distortion. But now using this design, what we did was, see, now it is much more controlled. Okay, it's not going haywire like it is going haywire, and this way that double inflection point was solved. The double inflection AMM distortion was solved. So this is the performance improvement. Um, you see that this one is without any source side non-linearity, and this is now with source side. This black line, this blue line is without source side non-linearity, uh, and this is now with the non-linearity. So, so once again, in order to validate this, you have to actually make the power amplifier. This is again the way we select the load from the load pull analysis. This is the actual circuit, okay, and this is the final power. So, so see, I agree that this is not, but this is the way it has to be done. Okay, I mean, in the sense that if you want a better power amplifier with a better efficiency, you have to go into these equations. Okay, so the first step is to develop an equation, a good waveform. You have to write the equation of the current and voltage in just mathematical. So the way we do, or what other researchers do, is that we first don't even go to the device side. We just write the equations of the current and voltage, just mathematically. Then using those equations, we try to find out whether it will give a better efficiency or not. And then we select a device which will actually implement the waveform. This is, in summary, what we are doing. It is not like analog design or digital design, where we start from the device first, isn't it? Suppose when we talk about analog design, say we are making a op amp, we first start with a common source amplifier, right? And then have load, either a resistive load or a PMOS load, like that. So there we directly relate our output to the circuit. But here it is not like that. Here we totally calculate everything beforehand. Before even putting the device, we write the equations of what should be the device current, what should be the voltage, device voltage, and using those theoretical equations, we find out what the efficiency should be. And then once we are convinced that yes, our equations for current and voltage are correct, we then try to manipulate our device so that it is forced to produce the current and voltage for which equations we have written. So this is kind of the way it happens. Yeah, that's all I have to say. Yeah, do you have any questions?
Sir, how to develop that equation which you have taken?
So as I said, that's why this work was done previously. Yeah. So as I said, if I go back to the, like this work, this was a paper published in 2019, where actually these equations were given, and we started from there. We worked from there. So it's not that we totally invented, no. We sort of worked on it more. Okay, thank you.
requested to ask any queries if you are having.
Thank you, sir, for this really nice experience. I'm sure everyone has gained knowledge about designing issues in power amplifiers with respect to the efficiency as well as design tool load post analysis. I again thank you, sir, on behalf of Electronics and Telecommunication Department for coming all this way to our college. Thank you.
साइड पर एक बार अलग यहाँ पे